Okay, so like I was talking about, Doppler effect is what, or what is the speed of sound in air? Do you recall?
343 meters per second.
343 meters per second, and it varies based on your altitude, it varies based on your density, it varies based on your temperature, and that's essentially why the temperature scale was there, right? Now, what happens is that if this sound source that you're looking at is going to produce a sound, that sound is going to travel 343 meters in 1 second, right? Y distance is speed into time, and the speed you set is 343 meters per second. Now, for instance, let's say that this object or this sound producing object is starting to move as well. What happens is that as this object is going to move, it's going to cover some distance, and that would produce, or that would create, an artificial wavelength. If let's say I had this observer that was standing some distance away, right? So he'll hear, or she'll hear, the first sound, and then the second sound would approach the observer a bit quicker, right? Or that wavefront would observe, or would reach the observer much quicker because the source is moving, and that creates this artificial frequency. And essentially, what that artificial frequency is, although this sound source was producing a sound at a given frequency, because the wavelength has kind of decreased because the source is moving, what happens? What happens when you've got the wavelength that's decreasing because the source is moving? The frequency is going to increase because the times required to produce one full wavelength. Remember, for sound waves, what is a wavelength? It's the distance between two compression waves, or two wavefronts, right? And that wavefront is where the location of that compression region is, right? And compression was what? Compression in sound waves is where all the particles are kind of stuck to there or pushed together, right? So as the sound source is moving, the wavelength between the wavefronts is decreasing, because although the frequency is the same, this creates this smaller wavelength in order to incorporate that. Because remember, the two rules were that the speed remains constant within the medium, and your speed is, well, given as, what is the formula for speed? Anyone recall?
Distance divided by time.
Distance divided by time, or in terms of waves, it's more to do with the frequency of the wave and the wavelength of the wave, right? So as your frequency is increasing and your speed of sound is constant, your wavelength is started to decrease, right? Or since your wavelengths are decreasing, your frequency has to increase because it has to follow this rule that the speed of a wave remains constant within a medium. So what that creates is, this creates this artificial frequency increase because the sound source is now moving, and that's what you observe in your safety vehicles as one example. And that's what happens to your your jet airplanes when they go supersonic, and that's a different thing, but it's essentially to do with what's happened to the air and how it's being pushed, right? And that entire thing was the Doppler effect. The next thing that we talked about, and that's not included in this slide here, but after Doppler effect, we talked about the intensity of a sound wave, or intensity of a wave in general. Anyone recall what intensity is? Well, intensity was the rate of energy delivered, or the power delivered by a wave per unit area, right? And remember, when we were talking about sound waves, what we talked about is that if you were to consider it in a 3D nature, or in a three-dimensional form, what happens is that the sound emanates in all directions, right? It's a pressure wave, and pressure is exerted in all directions, so the particles are moving in all directions. So it would create this artificial sphere around you. So the further you are, the sound wave is going to do what? What is a sound wave? It's a wave, right? So the wave is what? Wave is your energy disturbance or your energy. So the further you are from the source, that energy is divided onto a larger area. That's why the sound intensity diminishes as you are moving further away from the source, right?
Right.
Okay, thank you. So the next thing that we're going to talk about today was to do with, well, loudness. Loudness is kind of related to the intensity, and it's more importantly it's interrelated to the frequency as well. So the lower the frequency of a sound wave, you have to have the higher intensity to produce or make that sound audible. So the higher the frequency becomes, your intensity delivered is going to be what? The intensity is the intensity required to make that sound audible is much less, because you're doing what? What was intensity again? Intensity is the energy delivered per unit area. So now if I'm increasing my frequency, that means I'm imparting more sound waves or more wave fronts or more energy is being delivered to the source. So you don't need to provide as much energy to the sound to create that audible response. So if you increase the frequency of a sound wave, what happens is that there's more energy being delivered to the location, or to the observer, to the sink, or whichever way you want to talk about or think about it. But since the frequency is more, what that means is that the distance between the wavefronts is much less, and that means that more energy is being delivered to the location where you want it to be delivered per unit time. And that what means is that that this audible response that you see, this little dip here, that your area where you can start hearing things is much lower in comparison to, well, a sound wave which has a very low frequency and a low intensity, right? And above that there's a limit, there's a threshold, which means that it's kind of it becomes unbearable for humans to hear. And that's usually where, so remember that loudness scale that I showed you in your previous presentation? Not to you, but I believe that's included in part 3. That's the decibel scale, right? So the 20 hertz scale, or where the leaves, or the 10 decibel scale where the leaves were rustling and all of those, that might be somewhere around here, right? But that threshold of pain was something to do with the jet engine, or if you're standing close to the jet engine and that whine, that constant high pitch sound, that's to do with this little threshold of pain, right? And that was kind of where that 150 decibel sound level came in, right? So the next thing that we were going to talk about was to, well, talk about harmonics. And harmonics was essentially to do with a standing wave. Now, what we done, or what we talked about as standing wave, was that if you were to take a string, and let's see if I can find a string here. But essentially, in order to create a standing wave, what you had to do was, well, you had to, let's do this. So I've got this USB cable here. So I've got this clamped up on either end. One way to do it would be, well, that I create this little, what do you call it? So I kind of clamp it on either end. Can you all see me as well, or no?
Yes, we can.
Right, so what was it for a standing wave? That you clamp it, for a string at least, you clamp it on either ends and then lift it up or push it down from one end, and what that would do is that would create an antinode at that location. And once you release it, what would happen is, through the principle of superposition, this string or this wire would oscillate about its position, right? And that would create a standing wave. Now, there were multiple ways of doing this, and the other way was to, well, you have this pushed up, but you create an antinode around here, and then you push it down from here, and you kind of create this little sine wave, right? So you've created two antinodes, and in doing so, you've created a third node here. I would still oscillate about its original position, and what that means is that you're doing what? You're creating standing waves. Now that first one where you just created that antinode, single antinode, what that means is that's your first harmonic, right? And any standing wave that creates that first harmonic, or is associated with harmonics. The reason is that for a stringed instrument, you would like to have the ends of the wire clamped. Why would you prefer to have those wires clamped, or why would you prefer to have them have nodes at the end of a string? So think about it in terms of a guitar. What's happening with a guitar? Guitar's got its either ends of the string clamped or fixed. What does that do for the guitar?
Makes tension to make sound.
It makes tension, but essentially vibration is what? Vibration is energy being transferred from you to the strings. Now once you create that, or once you play a note on it, so on the fretboard, you're doing what? You're adjusting that length of the wire, and that's giving you those but those different notes that you can play on the guitar. But in doing so, you're clamping it, and once you pull on the string, you've created what? You've created different antinode location, right? So once you pluck the string, you've got two nodes on the ends, and then you've got a series of antinodes and nodes in between. But by creating those nodes on the ends of the string, what that means is that once that energy travels through, it transfers instantly, or all of that bulk energy is being transferred to the body of the guitar or the violin or whichever wired object that we're playing or musical instrument that you're playing. And in doing so, what you've done is you've transferred the maximum energy possible to the guitar body, and that then resonates and produces that sound that you're able to hear. Had it been another way, what you would get is you may get a destructive interference on one of the ends of the clamp string, and that full energy may not go through, right? And that's that. Essentially, this first little harmonic or this utilization of this two nodes and one antinode to create will give you your first fundamental frequency, and that's given basically it's the velocity divided by 2 times the length of the string, right? And that's your first harmonic. Now you can have more of these by essentially, well, creating these nodes and antinodes in between the string. The important part to know about harmonics then is, well, in order to, or when you're creating harmonics on a stringed instrument, you have to have nodes on the either end of the string, because you want maximum energy being transferred from, well, once you pluck the string, and that transfers to the body of the object, and that produces a sound, right? So your second harmonic is essentially twice as much as your first harmonic, so 2 times V2L, and your third harmonic is basically 3 times the first harmonic. So you're essentially creating what? How many antinodes in this case? Let's go one slide behind. How many antinodes were created within the first harmonic? Any idea?
Not sure.
Right. Let me share this. Can I launch a... Right, hang on. Let me stop presenting for a bit, and then let me share this document with you. Right, let's see, how can I share this document? Here we are. Choose from Drive. Let's see. right? I've shared a whiteboard with you, or a Jamboard with you. Are you all able to see that Jamboard? Yes or no?
Yes.
Yeah.
Okay. Well, so now what we're trying to do is, remember, we were talking about standing waves. A standing wave is what? By trying to clamp either ends of the string, and that would create this little wave. So the basic one is that you stretch it, you clamp it on either ends, and then you pluck it in such that you create this little antinode here, right? So you've got nodes on the either ends and antinode in between, right? And this gave you your what? Your first fundamental frequency, or F1 is equal to, well, basically velocity divided by 2L, right? Where 2L, this is your wavelength, right? Why is this my wavelength? Because a wavelength is supposed to have a crest and a trough. So now this is only your crest, and this was the length of the string, right? So your first harmonic is supposed to have one antinode. Now once we move on to our second harmonic, what is going to happen is that you're going to still clamp the string on either end. So you've got nodes on the ends, but you push the string up and you create one antinode here, then you push the string down, so you've got another antinode here. So what you get here is a sine wave. So you've got 3 antinodes and 2 antinodes. So your second harmonic, which is simply 2 times V2L, or VF1, sorry, not V2F1, is going to be your second harmonic, right? So when we were talking about, well, that your harmonics are what? Your general formula for a harmonic is Fn, where n is the number of harmonics that we're talking about, is simply going to be, well, n of F1, or n times F1, or where F1 is the velocity of the wave divided by the wavelength of the wave, or the wavelength of the first harmonic in this case, or the first standing wave. Does that make sense?
Yes.
Okay. Now let me switch back to the PowerPoint, and let me present that now. So your harmonics are essentially to do with your nodes, and in that case, what you're getting is, well, if you're talking about the first harmonic, you've got one antinode. If you're talking about second harmonic, you're going to have 2 antinodes on the stringed instrument, right? Now this is also utilized in your, or harmonics are essentially utilized on your organ type instruments, so your flutes and your saxophones and your organ, church organs or piped organs and all of those things. And essentially what you're doing there is you're doing the same thing. You're still creating standing waves, but the difference there is that you're switching your antinodes, or sorry, nodes with antinodes. And the reason why we do this is because in a piped instrument, you want your maximum amplitude to be released in the air, and your max amplitude for the wave occurs, well, where your standing waves antinode is. Does anyone have an idea why we're talking about standing waves when we're talking about harmonics? A standing wave allows you to do what? Or why does it?
Your sound.
What was that? Sorry, Trinity?
Your sound.
Yes, sound is one thing, but more importantly, what a standing wave allows you to do is that it creates this series of constructive interference and destructive interference. And wherever that constructive interference comes in, you get your maximum possible amplitude. Now that maximum possible amplitude again is to do with the energy of the system. So the more energy you have, the higher the amplitude will be. Now once you get that constructive interference, what you're utilizing is then you're utilizing the energy transfer that you did for the first pluck on the guitar string. So you gave it some energy, but then the reflected wave comes in, it creates that constructive interference, and that max amplitude increases, or that energy kind of is not lost. So that's why we're trying to use standing waves to our benefit now, that the string doesn't seem to move back and forth, although the waves are traveling on it. So the string is still oscillating up and down from its original position. But in doing so, we're utilizing the constructive interference part to release the maximum energy, or transfer the maximum energy in the case of a guitar or a stringed instrument to the body of the instrument, or in case of instruments that utilize air pressure to create, or air pressure to create sound, so your organs or your trumpets or saxophones or whatnot, all of those essentially, because they're not transferring any energy to the body, or they're not resonating the sound per se, what we're trying to do is that push of air through that body or through the instrument is going to do what? It needs to transfer its maximum energy out or to the air. And in doing so, for a pipe-based organ, what that means is that you need to have your max amplitude being released, or max amplitude sound wave being released into the air. And that's why this entire situation is kind of switched over. So in a stringed instrument, you're clamping the ends of the string, so you get nodes, so your maximum energy transfers through the body, where then it's resonated. In a pipe-based instrument, what happens is that you want to release maximum amplitude sound wave to the surrounding air, so the max energy can be heard. And in doing so, you have to create antinodes towards the end. Right? So let's go back to the what do you call it? The waves Jamboard that I shared with you. Let's go to a new page. So in this case, what we're trying to do is we're trying to create, so let's say that this is your piped organ, right? So what you're trying to do here then is you're trying to create, or the first harmonic is still going to be given by this little location here, but this is going to be your antinode, and you're going to create a node somewhere in between, and then you're going to create another antinode here, right? So essentially you're going to start with your max amplitude right here, you're going to reach 0 amplitude here, and it's going to be released back that way, right? Your formula still stands, your fundamental frequency is still, well, velocity over the wavelength, where the wavelength for this thing is going to be 2L. Remember, what do you need for a full wavelength? You need a crest and a trough. This only gives you one of those, so this is either a crest or trough, however you want to take it. There's going to be a remaining part which should be completed, and that should be the what? The remaining part of the wave. So your frequency or your wavelength is going to be, well, twice the length of this organ here, right? And that's your fundamental frequency. But essentially your frequency, or any harmonic in this case, or the harmonic frequency, is still going to remain the same, and that equation isn't going to change, right? Yes or no?
Right.
Okay.
Right.
And the last thing, and this is important because you'll need this in your the question that you have to solve for the harmonic at least, is for pipe-based organs but that are closed on one end. So the last thing that we were talking about, so this one right here that you saw, is to do with your pipe-based organs which are open on both ends, such as a flute or something. Now there are organs which have which utilize, well, a closed end as well. And that has to do with, in that case, what you've done is you've got a, so let's do that pipe based organ again, but you've closed it from the top, right? And in doing so, remember again, energy is what, or harmonics are what, that you're trying to create a standing wave such that maximum amplitude is being transferred to the air, such that so that no energy is being wasted, right? And we're utilizing the constructive interference to create that max amplitude sound. So that means that your reflected wave energy isn't being lost anywhere, right? So in doing so, remember this is the entrance for the air as well, and this is going to be the exit for the air. So again, you have to create an amplitude or antinode here, right? So you have an antinode here, but you have to create a node on this side. Why? Because, well, remember again, for the first harmonic, the frequency is going to be what? That you have to have your max amplitude again here. So what would happen here is that you would start from here, the wave would reduce to, let's try a different color. You would start with your maximum amplitude here, right? And it would reduce down to 0 amplitude here, and then kind of rise back up, right? And in doing so, it would kind of follow this little, let's try it one more way. Let's try it that, so let's try to plot it. So what would happen is that you would start at your maximum amplitude, you would get to a node here, so this is the node location, then it would fall back, and that's going to be your next antinode. So it would create this little wave pattern here, right? And that would reflect back and come back here to create that antinode here. The fundamental frequency though is going to change to what then? If this is the length of the object, what has happened? In order to create one full wavelength, it has to do what? It has to go through 1, 2, 3, 4 oscillations. Remember again, a full frequency is going to have either 2 antinodes or 3 antinodes depending where you're starting from. So if your antinodes are the clamping points for an open-ended sound instrument, you're going to have 2 nodes in between, or if you're trying to do it with a clamp string, you have to have, well, for a full wave, you'll have 2 antinodes, right? So in doing so, your frequency now changes to, well, 1 by 2, or sorry, not 1 by 2, but velocity over 4 times the length of the body or the piped organ that we were talking about. I'm sorry, you should be here on this page. Right, so your fundamental frequency for a closed-end pipe is given as V by 4L, right? And only odd frequencies are present in your closed-end organ. So the next frequency is going to be, well, the third harmonic, right, which is going to be 3 times F1, or the one after that is going to be your fifth harmonic, and that's going to be, well, simply 5 times F1, right? And you'll need this for the first question on today's assignment. Right? So now let's move on to, this is kind of the end for harmonics, or this is the end for the sound waves. And sound waves are essentially longitudinal waves, and we've talked about quite a few things that happen that are related to sound waves. Now we're going to move on to, well, light waves. And this is essentially what I've shown you in your little Jamboard, and then how you're getting to these things. The next thing that we're going to talk about is, well, light waves. And light waves are essentially to do with what? They're transverse waves. They're electromagnetic waves. Electromagnetic waves then means that, well, we're talking about an electric field and a magnetic field. They're both working, or a light wave has both of these things. A light waves the definition changes, right? The definition changes, and we're going to talk a bit about it. But essentially, light waves are electromagnetic waves, and they've got both a magnetic field and an electric field, and they're alternating between each other, or they're perpendicular to each other. So they're both present at any given moment, but they're kind of 90 degrees to each other. A light wave, again, remember what we talked about. What does a wave require? It requires a medium to transfer energy, right? But a light wave, on the other hand, uses, what does a light use to transfer energy? Anyone? What does a light require? Or since energy requires a medium to transfer energy, or since waves require a medium to transfer energy, and sound waves, they're going to travel in this air around us, are you able to hear sound in vacuum? Yes or no?
No.
No, you're not, because there's no air particles to create those compressions and rarefactions, so you don't hear a sound in the vacuum of space, right? But light still travels through space, right? But there are no particles in space. So why is light able to travel through space? Or what is light then? Any idea? No? Well, light travels through what's known as photons, right? Or a light is transferred through or emitted through photons or via photons, and photons are a special category of massless particles. And they are present within the vacuum as well, and that enables how wave is, or how energy is being transferred through the vacuum of space. And that's what was kind of, if you start researching a bit more about Einstein, is that after the video that we've watched about that gravitational, or that movie that we've watched about gravity, regarding Einstein and Eddington, and their 1919 research that they've done. If you move on further, you'll kind of find how Einstein has been, through his later years and research, he was working with light, and how the photon discovery and how all of those things came into being, right? And there were theories that were being proposed. So there was that character of Planck in there that was played, and he was one of those initial proposers of the theory that light is being used, or light is traveling through photons, right? But essentially light is a wave, and it's a transverse wave, which means that the particles, or in this case, are oscillating perpendicularly to the direction or the travel of the wave, right? And light wave is, more importantly, an electromagnetic wave, and it's got both electric properties and magnetic properties, and those waves, or the electric wave to the magnetic wave, is at 90 degrees to each other, right? And then remember, we talked about this at the very first during the very first lecture, when we started talking about light. That light is, so your visible light is this little narrow zone right here, right? And that narrow zone has a wavelength of, well, 10 raised to the power -6, or some micrometers, or less than a micrometer even, because it's 0.5 here. But beyond this, you still have your electromagnetic waves, which includes infrared wave, and that reduces to, or that wavelength increases to, a microwave. And then there are radio waves, right? That's why radio waves are being used for communication. Why are they being used for communication? Because your wavelength is quite large. And what that means is that you require less energy to make a wave travel quite a fair few distances. So your radio waves have a larger wavelength, and that's why they're used for communication. Now, on the other hand, that means that your X-rays and your gamma rays, which are after the ultraviolet scale, they have a very small wavelength, and that means that they carry more energy, but they are unable to travel longer distances because they lose energy quite quickly. Right? Or in other words, you could have a look at this little chart here where you've got a higher frequency with more energy. Why again? You've got a higher frequency, that means that more energy is being imparted at a very small time interval, right? On the other hand, the longer wavelengths, you give them a little bit of energy and they're able to travel a lot longer, right? And that's where your AM waves and your lower frequency, I haven't seen that used, maybe in the military channels they're using this, but then you've got shortwave radio, TV and FM, radar, microwave, infrared, and all of those things. Visible light is this very narrow band, and that creates our light that we see, right? But more importantly, light waves are still waves, and they're going to reflect when they're going to pass through a medium. So when we are looking at colors, that is essentially what? That all of the light waves that are traveling, so if you're shining white light onto anything, when it shines onto a color, what that means is that all of those light zones, or the visible light zones, so remember the 7 colors that we saw in this previous slide here. So your violet, indigo, blue, green, yellow, orange, red, all of those colors are combining together to create white light. But once that light passes through, so let's talk about leaves. Leaves are green in color, so every other color apart from green is absorbed, but the green color is reflected back. Right? And that's how we see colors today. That's using those 7 main colors, or 7 basic colors of visible light, to create the colors that we see, or to create the different shades of colors that we're able to see these days. Right? Your computer screens are able to differentiate between 256 colors, right? And that's why you get this 256 color gamut that you see when you're looking at different images, or when you're setting up your computer screens. On the gray levels, we're able to see about 16-bit gray color, so your white and black is differentiated into 16 different zones, and the higher that is, the better picture quality you're going to get when you're taking images. So all of those things is to do with light waves, right? But in our case, we're going to be talking about light wave reflection. Light wave reflection is going to occur through mirrors, and there are 2 types of mirrors that we're going to, well, we're just going to discuss them briefly, but either you're going to have a very rough surfaced mirror, or you're going to have a very smooth surface mirror. And where we're going to use a rough surface mirror, that means that the light waves are going to come in and they're going to kind of bounce off everywhere, right? And that's known as a diffuse reflection. On the other hand, where you've got a smooth mirror, your light will come in and then it will be reflected back in another direction, and that's going to be known as specular reflection. And for all cases that we're going to talk about, we're going to be working with specular reflection, right? And when we talk about smoothness, that smoothness is more to do with, well, what's the difference between the wavelength and the scale of the roughness of the river, or the surface of the mirror in this case. Now that surface variation that we're talking about has to be much smaller than the actual wavelength of the incident light wave as well. So let me go back 2 more slides, and remember here, what is the wavelength here? It's given to you, it's anywhere in between 100 nanometers to 1,000 nanometers. What does anyone remember what nano stands for? 10 raised to the power what? Nano stands for 10 raised to the power -9, and that's your on the nanometer scale. So the smoothness then for a mirror is, well, going to be much smaller than that scale that we're looking at, So it has to be very small compared to that nanometer scale, right? And whenever that happens, what you'll see is that the incident ray of light that is going to come in, it's going to be reflected back, and it's going to reflect back at a given angle. Now it's going to reflect back, and that angle is usually the same. So your incident angle is going to be the same as the reflected angle, and the way you find it is by drawing a wave or a line that is perpendicular to the surface of the mirror, or the line that is at 90 degrees to the surface of the mirror, right? Any questions?
No.
No.
No? Okay, just to wrap things up, what that means is essentially that if your incident ray was traveling at 30 degrees from this normal, your reflected angle would also be, or the reflected ray of light would be also be reflected at 30 degrees from this normal, right? Or this angle right here is going to be the same as this angle right here. Does this make sense?
Yes.
Okay, right. So let's stop here. I believe you can. There are 3 questions on the assignment that's been posted. You'll only be able to do question number 1. That is to do with harmonics. Now tomorrow, what I'll be doing is I'll be recording the video again for part 5, and that's going to incorporate whatever is left on this PowerPoint and the one that is designed for tomorrow. And that's all to do with, well, light wave reflection, lenses, magnification, all those things. And once we're done with all of that, that's going to be the end of this chapter before we kind of leave for Thanksgiving break, right? But since I won't be seeing you all tomorrow, you'll only have a video. Please let me know if you've got any questions. Please email me. Other than that, have a very happy Thanksgiving, and I shall see you all on Monday, the 30th.
Happy Thanksgiving.
Yeah.
Thank
Have a
you.
good Thanksgiving.
Thank you. Bye-bye.
Thank you. Happy Thanksgiving.